So we started with error calculation. We had two types of error. We had approximate error and we had true error, okay? And the approximate error, it was the error which is found with respect to the newly found value. So when we use iterative techniques, we have the newer value is allegedly a more correct one, which means that that will be used as a reference when we calculate the error. But a true error is a value that we do know, and in that case, that would be a different kind of error. We know, we have observed in this class that sometimes, I mean, probably often or a few times, the approximate error, it is gradually decreasing, but the true error, it might fluctuate, which means that true error might increase at some subsequent step, and in the next step, it might decrease again. But the approximate error, it has a more defined feature of how it's changing. So it's gradually, it keeps decreasing gradually. And after that, we started the course with root finding. Okay, in root finding, if you, I guess you do remember, we started with increment search method, ISM, incremental search method. And after the incremental search method, we started with the bisection method and so on. And then, let me see just for a moment. Okay, we did bracketing, open method, and one of the most common techniques, which it should be the last one to forget for all of you, would be the Newton-Raphson method. Okay, probably you won't forget it, but Newton-Raphson method is a very common technique which is used for the root finding, and it has a very fast convergence, or it converges relatively faster than the other techniques. Then, after the root finding, we covered the methods to solve systems of linear equations. I think in the previous final exams that I have submitted, and let me check just. And by the way, I just want to check if my microphone is on. Apparently it is on, okay? I hope you can hear me, yeah. Okay, because sometimes it happens that things, we may not be, I might have forgotten the microphone off, we are good. So then we started solving systems of linear equations, and I'm pretty sure that you have seen some of these approaches when you took the linear algebra course. But here, something new that we learned, it was the iterative techniques, okay? So with the iterative techniques, you have learned how a vector, not now the same way or in a similar way that you used to find the roots, now you have a search vector, and this vector is composed of x, y, z, if you have three unknowns. And these three unknowns, they are the solutions of an equation which is equal to ax is equal to b. Okay, so this would be the so we had this ax is equal to b. This was the type of the systems of linear equations that we had to solve, and then we covered interpolation. We covered interpolation, and in interpolation we started with the Lagrange interpolation, and then we did also the Newton method. Then the last part of the course is that we covered the numerical integration and numerical differentiation, and with these two techniques we saw actually how we can approximate those, and we, for both of these two techniques, we learned something which is very useful, which is really essential or very important, is the Richardson extrapolation. So we could prove that the error in numerical integration and differentiation is of the form which looks like this. So the error as a function of h it's something like OH squared, and probably I can so the error is of this form, and this means that this is approximately equal to A1 H squared plus A2 H to the power 4 plus A3 H to the power 6. So this is the error. If this is the error, we know that these values, they are well-known values. Okay, so these are some coefficients, A1, A2, and A3. And the technique of Richardson extrapolation, what it does is that we try to find A1, and we substitute A1, and then the rest is an error which belongs to the next order, which is of the H to the power 4, and so on. And this Richardson extrapolation, we learned how we can do this one in a series of iterative approaches, and these improvements, we follow them as the H, it progressively gets smaller and smaller by a factor of 2. Okay, so remember this, the Richardson extrapolation. Richardson extrapolation for numerical integration and the numerical differentiation. And then we did also the differential equations. Now, regarding the differential equations, I guess we spent some time in there, and we were trying to solve these types of equations. Okay. And the idea, the solution, it was always of this form: y t plus 1 would be equal to yt plus the function of yt pt times delta t. Now this delta t, this can be considered also as the h. So h, we determine, or we call the step function for which we change the independent variable, okay, not the dependent variable. And we know the independent variable is in principle the x value, the horizontal axis, y is a dependent variable, and so on. So these are mainly the topics that we have covered during this semester. So in the final exam, you may expect to see error calculations, okay? So we are going to report approximate error calculations or true error calculations, stating like the error is in the order of 3%, 5%, 10%, okay? And you might expect also questions of to look for a solution of linear systems. I always like to have the Taylor series expansion over there, okay? So you might see how a question might come up with that. You can also see the previous final exam questions that I have posted on Google Classroom. And yeah, so do you have any question? I can invite you.
Professor, are Runge-Kutta formulas included in the final?
You're asking about the formulas?
Runge-Kutta.
Oh, okay, let me think. You're asking whether you need it or
whether we're going to be asked to solve exercises using Runge-Kutta.
Okay, in case we ask something like Runge-Kutta, I might provide you the formula, the steps, okay? Because it's not something that you are always asked to memorize it, but I might provide, in case of these types of questions, so I will provide the formulas, okay, or the steps that you need to do. You can assume that you don't need to memorize much, okay? And now, regarding the Runge-Kutta method, whether we ask it or not, what is essential is that the Runge-Kutta method, it makes predictions in the future as we progress along the x-axis or along the independent variable. And we know we have a delta h or a delta t if the variables are changing as a function of time or t. And then we try to predict the future values or the subsequent values using the slopes of the function in the future, okay? And we don't use only one slope, but we use 2 or 3 different slopes, okay? That's something that we need to know. Regarding whether we ask a question like that, I guess once you are provided the, what's the name? The formulas, I guess you could do well on that, okay? So there is some, yeah. Yes. Any other question?
Maybe we could also get the solutions to the exams you've posted in Classroom, so we can check ourselves.
For the final exams that I posted?
Right, and we could get the solutions so we can see our mistakes.
Okay. I can check, I should check, and I could have them somewhere, or I'm going to solve them, okay? But I strongly suggest you to go over those, okay, to solve them. If you have any question, you can always ask me about the questions of the previous exams. I see a couple of questions in the comments section. I see, yes, Anilidio, the final is going to be similar. You might notice that in the previous exams, they belong, even the course code is slightly different. The course curriculum was slightly different. The singular value decomposition in the previous semesters were taught in the last part of the numerical analysis method. So if you see these types of questions over there, that's the reason, okay? But now we are not going over these advanced or semi-advanced material of linear algebra. So those questions you can skip, but skip in terms of we might not be asking explicitly find eigenvalue, eigenvectors like in the previous exams, but it's something that you should know, okay? It's like also an exercise for you. Gauss Quadrature or Chebyshev? Oh, okay. Chebyshev, you mean when we use the Gauss Quadrature? Well, I will provide, if you need anything to implement the Chebyshev method for the Gauss Quadrature, I'm going to provide the cheat sheet. You don't need to bring anything, okay? Now, Gauss Quadrature, the way that we covered here in the class, we also aimed to make it by a couple of examples or one example. We try to make it clear why we need it or why it is so useful. Okay, that was my main intention. But again, over there, if anything like that comes up in the final, we're going to provide the cheat sheet for it. Okay, because those tables you cannot memorize the critical points. Okay, because you have to determine the critical points and some coefficients. You'll be given those. Okay. But I strongly suggest to go over the recordings when we talk in the class about the Gauss Quadrature. It's a good review. Okay, you can go over it and have a look. Any other question?
Sir, could you provide a list of topics that we should focus on to study for the exam? Because in the case of iterative techniques, in multiple occasions there are multiple techniques. Can we maybe know which one to focus on, or?
Well, how can I say? I guess when we started today, so error calculation, be ready for it. Okay, you cannot have an exam in numerical analysis where you don't do error calculation. Well, I mean, the topics are out there. You have to go over the numerical differentiation, numerical integration. Have a look at the Richardson Extrapolation, how we implement it. and the level of difficulty. You can see the previous exams how Richardson extrapolation can be asked in a final exam. And let me think. Root finding, okay. I mean, no, Amalia, no, it's not going to be asked. So you asked about Octave? No, it was just a tool which made me easy to run during the course without running any other complex programming language like MATLAB, which is going to kill the memory, which was going to kill the memory of my laptop. Okay, so no programming will be asked. All of the calculations will be using a pen and paper. Yeah. So now, regarding the review of the topics, I think, well, I mentioned those. So, I mean, you have to go over root finding, solution of linear systems, yeah, error calculation, numerical differentiation, numerical integration, differential equations. And I suggest if you skim through the class recordings that we have provided, and also the class materials. Actually, this semester, since I was forced to do the course online, this was my best semester in terms of PowerPoint presentation. So even all the PowerPoint class material, they are on Google Classroom. So I expect you to skip them, whether you read them very carefully or not, but you should have a look of what we have gone over in the class, okay? So it will be a very, so it's like a minimum, okay? Studying for class material, of course the textbook, I follow the textbook because it's always good for the students to have a textbook where we follow a certain structure without jumping from one topic to the other. I rely a lot on the book because it's also a good bit for you. But please go over the PowerPoint notes that I have left for you. Okay. Now interpolation. Interpolation, yes. I mean, the interpolation will be as much as material that you can find on the slides and on the previous class recordings. Okay, Kevin? Now, Fourier approximation, no, because Fourier approximation we did not cover as a class material. It's through the couple of projects that were assigned. Some of you had to use some techniques, some major elements. But it's a final exam. Go over the PowerPoints, okay? They are the best PowerPoints I've ever had in this course. I mean, material which you can easily collect the lecture material in a short space or in a concise manner. Yes, Argus, I can prepare a list of the topics. I guess our exam is the first one, well, at least it's on the first week, right?
No, the timetable has changed.
Or okay, when is the final?
It's in the last week.
Oh, okay. So we have a little more time. I thought initially it was on the first week, I guess, right?
Yes, but it changed with the database exam.
Okay, yes. Okay, so it looks like you're gonna learn, you have some more time to study for this course with regard to the final exam time, but it will be the last course you learn the final grade, I guess. At least judging by my grading capabilities. Okay, thank you for updating me on this. And any other question you could have? Or that you may have? We have this iterative techniques. You know that we have this, we talked about when we had the made any equation which was written in the form of ax over is equal to b, we had some conditions for convergence. Do you remember what was one condition for convergence of a linear system of equations? Do you remember that?
It has to be diagonally dominant.
Yes, exactly. Yeah. So the coefficient matrix A is diagonally dominant, then for sure it is going to converge. Okay. So here we are. This coefficient matrix A times a vector x. This is equal to another vector B, which is the non-homogeneous part, which is the vector B. Okay. Okay, I'm going to put another list of the topics, and in fact, this semester, since you have all the recordings, it would be really a good review if you go over the recordings. Okay, so open the class recordings, have the PowerPoints material in front of you, and I guess this is probably also one of the relatively easier semesters to do the review. Okay, because we have not recorded so regularly the previous courses, so I guess you already have the material published somewhere. Okay, any other question?
Professor, in the topic of root finding, should we focus only on the Newton-Raphson method, or should we look over the section on false position methods too, or the simple fixed point iteration? The second method, because there are many methods provided. So.
Yes, we have a couple of methods. Well, we have also bracketing methods, the thing where you keep dividing the range where you have a candidate for a root. You keep dividing it by 2 each time. I cannot say that do only Newton method. Okay. So it could be second method. They are more or less relatively similar to each other. Okay. But for sure, I'm not going to ask 4 of them. Okay, probably I might focus on the most important one, like Newton-Raphson, because if I ask all of them, then we cannot cover the whole material of the semester. So I guess focusing on Newton-Raphson is a good way to say it. Okay, but I cannot say that second it won't be. Okay, don't read it, throw it away. But I guess you can predict actually if finding roots of finding a root of a function, you might predict where the question could come from. Okay. It's not a final exam based focus only on root finding, right? We have relatively good material. I mean, a lot of material to cover or to check in this exam. Any other question? Okay. Meanwhile, for any other question, you can always send an email, and we'll try to answer you whenever, as soon as possible, at least. Okay. Actually, the number of questions, I don't know. I don't know how many questions there will be, but you're going to expect at least 6. Okay, at least 6 questions. You might expect, so let me say also this one. One of the questions is going to be theoretical, where you have to explain. Okay, so there will be a couple of questions which you are asked not to use we have no calculations, but we have to explain things. Okay, so out of 6 questions, be prepared that one of the questions is going to be I don't know, conceptual questions, or that is asking for your understanding of numerical methods, and the other 5 or the other 6, they are going to be asking the different topics that we just discussed. Okay, which includes numerical differentiation, integration, differential equations, solution of linear systems, root finding. And when you do the root finding, it's always that in these questions you always may have to find or to calculate for each step the approximate error or the true error. Okay. Okay, so this is how you might expect an essay. Okay, any other question? Yeah. Okay, then. So if you don't have any more questions, how can I say? Go over the textbook. Yes, Anilia, I'm going to post it, okay? Because we have a few students that are not attending this review session. I will. Okay, so for, you mean Hermite, where we use for Gauss Quadrature, Amelia, right? Well, we could, but the thing is that is this way. So Gauss Quadrature is a good technique, which is based on, most of it is based on how to read carefully a table of coefficients and a table of defined values of x for which you are going to evaluate the function f. I guess we have at least like we have the Legendre method where we use the Legendre polynomial, the Chebyshev polynomial, the Hermite polynomial. So if we solve all of these, it will not be that all the questions will be on the Gauss Quadrature, okay? But I can remind you that any integral from a to b of any function f of x dx, this is going to be equal to the summation of some coefficients ai times the f of xi, okay? So this is the general, or what we have to do. Now, if you want to see, to go any example, let me think if I can come up with it. But if we come up with any example, you have to go to the PowerPoint lecture notes and find the coefficients for me, okay? Because I don't have the notes. But let me see. So you asked me about Hermite polynomial. Hermite polynomial, it's a special case when the a is equal to b is equal to infinity, or a and b, it converges to infinity for sure. Okay, that cannot be equal to infinity. And these coefficients. So let me think just for a moment. So let me ask you then. So Hermite polynomial, can you find the lecture notes? They were relatively good actually. So for what cases do we use Hermite polynomial? Amalia, do you have the lecture notes? Okay. So when we had these methods, we had an essential relationship, which was finding the relation between m and n. So if we had the integral, if this f of x, it was a polynomial of degree n, which means that here you can have f of x, it is equivalent to any polynomial in the order, let's call this one Pn, okay? So if this is Pn, then do you remember what is the relationship between the m and n? So this I, it goes from 1 to n. Okay, so this is how many terms we are going to have. So if we have a polynomial of degree m, n, we need to identify m different terms. And that's what we have to look for in the table, in the specific table. But now, what is this relationship? We have the m here, it should be smaller or equal than 2n minus 1. Okay? This is something that you need to know, or we need to figure out. And if this function f of x, which we want to integrate, so this a and b is from minus infinity to plus infinity, then if you give me a polynomial, let's say it's of the third order. If it is a polynomial of the third order, that means that this is P3, okay? And the m, it is smaller or equal than 2 times 3 minus 1. 2 times 3 is 6 minus 1, 5, m is smaller or equal than 5. Now, we go with the smallest numbers, the smaller or equal, so we go with 5. So it looks like we need to find, in the table of the Hermite polynomials, when we have these coefficients, we have to look for n points, okay? And then, if we go over there, so any one of you, you are like a good number of students in the lecture notes, where we discuss the Gauss Quadrature. Can you find the table which includes the coefficients for the Hermite polynomials? If you cannot, I can go over to Google Classroom. But out of 20 students, for sure, there is someone faster than me to find those. So in the Google Classroom, you can numerical methods, because it's not something to memorize. And this polynomial, you can give it any shape. Poi je ben 3ai de 3xi. Poi do tiem PS. We need 5, Amalia. Because the polynomial is of the third order. If the polynomial is of the third order, that means that, wait a second. Okay? We need 3 maybe, wait a second. So in this case, do you remember, maybe you are right, Amelia, let's check this one. So, let me think this problem once again. It looks like this is the degree. No, okay, this should not be so bad. What I mean so bad is that the number here is normally smaller than the n, okay? So it looks like I made a mistake here, okay? So normally, we have optimized a lot these numerical techniques. So if the polynomial is of the fourth order, I should have noticed this one. So probably this is the other way around. This n here, which I assume that we have a polynomial of the third order, then it looks like 3 should be here. Yeah, 3 is here. And this should be smaller or equal than 2n minus 1. I guess you gave the right answer, Amalia, so they have to have 3, right? Let's see what we get here. Let me make, this is 3, this is 4, or even 2 actually, 2n. So it looks like this n is equal to 2. So in the table for the Hermite polynomial, so this part, this is wrong, okay? Correct this part. This is more right. And we are doing this assuming that this f of x is a polynomial of the third order. Then, present now. Newton-Raphson. I don't remember which week we covered this. Root finding, no. Examples. So, week 5, 1. Or, Okay, anyone of you found it already? I expect someone being faster than me. Okay, so I'm not sure. Here we have an example where we use the Gauss Quadrature, but I'm expecting to have another class. Where is the crown? Okay, here we go. So here we talk about the numerical integration. I guess in this class recording, we may find, because I cannot find the PowerPoint right now. Okay, that's what we need. So we need to look at the orthogonal. This is Gauss legendre. So again, if you are taking notes, you can write down that if we want to integrate any function of the third order, we need only two nodes. But if you want to solve it using Hermite coefficients, let's see where the Hermite is. Why can't I find it? Anyway, so let me see if any one of you commented in here. Week 8, Calendariat Analysis, Numerical Par. Okay, we found it. So it looks like for the Gauss-Hermite method, if we want to integrate a specific function, a polynomial of the third order, we need to get 2n. Okay, we correct our initial mistake, but you can always use this intuition. So actually, I calculated it. It didn't look very right to me because having a polynomial of the third order and using 5 nodes, this is too much. Okay, but it looks like this is a better method. So then this is going to be equal to, so if we're going to use 2 nodes, according to this, this material, it looks like the coefficients are 0.886, okay? So here we're going to be 0.886 times the polynomial evaluated at x equal to minus 0.7, and the other coefficient is again 0.886, okay? Plus 0.886 times the polynomial evaluated at the other value of x, which is here, 0.7 again. Okay. So this would be, for example, how we use the Gauss Quadrature using Hermite method. So we found this, and to have a better look, we are presenting. So the solution is going to be this. So you see that really this Gauss Quadrature, it really helps a lot because it simplifies. It makes and it also converges very fast. If we have a polynomial of f of x, we could also have any function which has singularities. This is also very amazing. Imagine you have a function which is not defined at all, but you can find the integral. And the answer then is going to be this one. Okay. And here, instead of this polynomial p, you can write any polynomial of the third order. If it is a polynomial of the fourth order, then we would have the following. We'll have here the 4 would be smaller or equal than 2n minus 1. Then this would be 5. This is 2n then divided by 2, this would be 2.5 smaller or equal than n. This means that n is going to be 3. So if we have a polynomial, so this is for a polynomial which is going to look like 3x cubed plus x squared. Okay, this is a third order. Here, if the polynomial is something like 4x to the power 4 plus 3x cubed, okay, you understand. So once you have the highest power, you understand that it's a P4. Then for this part, we need n should be larger or equal than 2.5. It should be an integer number. So then this means that here n was equal to 2. It's written here. Here n is going to be equal to 3. Okay? So we have one higher order for the polynomial, which we need to find the integral, which is given here. Then if you want to get the 3, you go here to the PowerPoint slides or to these materials. And it looks like we have to use n is equal to 3, which is, it looks like the values of x, they are symmetric with respect to the 0. So if I erase this part here, it looks like we have, this is the x-axis, and the node or the value of x for which we are going to evaluate the polynomial is going to be 0. So it's going to be this point here. It's going to be also plus minus 1.22. So we have here minus 1.22 plus 1.22. Okay, these are the nodes. We have to evaluate this polynomial at these three values, and then the value at 0, it should be multiplied with a coefficient of 1.18. So here we have 1.18. This is the coefficient, and the other coefficients are 0.29, 54, etc. 0.29. So here we multiply by 0.29. Okay, and this is also 0.29. So we got this much information. Then we come back to here. So then the integral of a polynomial of the fourth order, it can be something like this. So let's say that this is 4x to the power 4 plus 3x cubed. You can have more terms, plus 3x cubed. Integral over dx from minus infinity to plus infinity. Then this would be equal to 0.29, which is the coefficient, times minus 1.22. We substitute this minus 1.22 here. So this is, well, you can do that. So you can put here minus 1.22 plus 1.18 times the polynomial evaluated at 0. In this case, this polynomial evaluated at 0 is 0. Okay, if it had any coefficient, it would be better. But since we selected this, let's go with this. So this polynomial, when we substitute the 0, is going to be 0. This is gone. Then we have also plus the other coefficient, which is 0.29. And again, this 0.29 more precisely. It was 0.29 for 54 and so on. This is times the polynomial evaluated at 1.22. Okay, so we substitute all of these values, and here we have a Gauss Quadrature, or the calculation of numerical integration using the specific orthogonal polynomials, Hermite polynomials. Okay, so this is how we can use these. Okay. When I first learned about this, I was really impressed. Okay, I remember when I was a few years earlier, and yeah, it's a very useful technique. Okay, so this would be, for example, how we solve the Gauss Quadrature or numerical integration using these specific functions. Okay, any other question you might have? So Amalia, I guess this was, yes.
Will we have to solve the boundary value problems?
Let me think. No, you cannot. No, I think actually you could, but
Well, the numerical methods are kind of long to write in a paper. They are meant to be written as a program.
yeah.
So
Yeah, that's right. So actually, the boundary value problem, no. But let me add something here. So you can solve, in principle, boundary value problem. Let me ask you one thing, for example. It's an exercise. Probably you won't see this in the final, but it is so easy that you wish it was in the final. For example, and actually I mentioned this one. The numerical solution of differential equations is really one of the most useful, one of the most employable element that could find you a job if you're going to work someday, or if you go to some hackathons. Okay, these hackathons where sometimes you even get some prizes as university students to participate. Sometimes you may be asked to formulate a model. Okay. And this model, it could be something which the only way to solve it is the use of differential equations. Okay. Now, differential equations, you can make prediction of what is the value of y once you are given the initial condition. We cannot solve the differential equation without an initial condition, because solving a differential equation is solving this dy over dx, right? You are given something like this, and then the answer should be this: y is equal as a function of x. Okay, and solving this differential equation, it is equivalent to integrating. Okay, and the integration is the only operator which is the inverse of the differential. And we know that once you apply the integration like this, you need the constant of integration, and this is solved by given an initial condition. Whenever you solve this problem is given like this. You say dy over dx, this is equal, let me say this, 3x. Okay, this is a differential equation. Okay, but you need also to put here that y for x equal to 0 is equal to 5. Okay, this is a given. This is the input. Okay, so because you say, okay, I'm reading this question, but what is really the question? So what is given and what you need to find? So this is a given. Then, based on this knowledge, you have to find this. Good. So differential equations, they are, as I said, actually pretty useful. Now let's come to the boundary value problem. We can have let's say we can have the second derivative of y with respect to x. This is equal to, let's say, 0. Okay, so what is this? This can be even much more complex. In fact, these solutions, the solution of this one is in fact y is equal to cosine x plus sine x. That's it. And it can also be a little more complex, such as this can have constant c1 times cosine x plus a constant c2 times sine x. So you can try actually. You can get this value of y. You find the first derivative. You find the second derivative. You insert it here and check if this satisfies the initial given differential equation. Okay. And actually, this is, I think we have done in the class. If you go over the differential equation course, I remember we gave you the differential equation of this form, and you had to find out which one of the several offered solutions, whether they satisfy the equation or not. For example, wait a second. Let's make this a little more complex. Y, this is equal to 0. Now we can. This is also, wait a second. Sorry, I made a mistake. The solution of this differential equation, let me ask you actually, this is not the solution of this. But let's correct our mistake. What is y if this is the second derivative of y? The y, if we integrate this once, let me give you the answer actually. The y is equal to mx plus b. Okay. This is the solution of this, because this means that the second derivative of y should be equal to 0. What if the second derivative of y is equal to 0? That means that y is a linear function with respect to x. Or we have x to the power 1. Okay? And that's the only case. But, so this was it. But this problem here, this is the second derivative of y with respect to x plus y, this is equal to 0. Okay? We make a lot of mistakes in the class, but we try our best to correct ourselves. Okay, so now, yeah, this is a good pair actually. So now this is also an exercise for you. You get pen and paper and confirm whether I'm correct or not. Okay? Let this be y1, and you can try the first expression, which is cosine x plus sine x. Insert this one in here and see if the equation is satisfied. Then you can try the second one. So this is y2, okay? And you can also try this y3, this is equal to e to the power minus x. For example, what do you think? Is y3 a solution of this differential equation? Can you have a look? What do you think? Think about this one and check whether y1, y2, y3 satisfy this differential equation. So again, let me come to the initial problem. In the class, I guess we solved examples with boundary value problems. And the main objective was also to, because when we constructed it, we also discussed in the class how we solve this numerically. Okay? There are some details, which are beautiful details, that probably someday you might find them useful again. But we cannot formulate it in a final exam. Okay, we could, but it could be something like this: confirm which one of these is a root of a differential equation. And I cannot say that these types of questions are not going to be asked in the final. Okay, this is the same like saying this one: 3x is equal to 6. Check which one is a true solution. Is it 2, 3, 1, or minus 1? Okay. You just try, put the x in this equation, you confirm which one is true or not. The same thing, you can do it here. Given the differential equation, the options that you might be given, check whether they do satisfy the equation provided to you. Okay. For example, this equation here, the solution, you're going to follow like this. Okay, you write this expression. What is h? Now h, you can choose it. It can be 0.1, it can be 0.2, it can be 0.5, it can be 1. But we know that smaller the h, smaller the error is in predicting the future value of y. So then in this case, for the specific differential equation which is given there, it looks like the solution, it will be constructed like this. We are given y at x is equal to 0 is equal to 5, so this is 5. And then we have to figure out where, if the h, let's assume, if h is equal to 0.5, which means that the incremental step along the independent variable is, if it is 0.5, then the question is, where is this, the next value of y? So we're trying to construct a graph, actually. Okay? We're trying to determine these points as a function of x. So we're trying to find a function, or we're trying to draw the graph. Maybe the better way to interpret it is trying to draw the graph as x is increasing. Okay. Okay, any other question?
Will we have in the final a question such as the one you posted in homework 4, the matrix, with differential equations?
Let me.
We had to convert.
Probably, no, probably might don't expect something like this, but no, don't. Let me say no to this.
All right.
Yeah. But I think it's really a very beautiful and elegant way to solve differential equation using matrices. I find it also a very good way to solve it because it also educates all of us important concepts such as diagonalization. Now you are in the second year. Okay, next year when you go to the third year, you are going to see little more advanced topics where the major topics will be PCA or principal component analysis. You have PCA or principal component analysis is enough, or dimensionality reduction. Dimensionality reduction, you have also the covariance matrix, covariance. In fact, you might see covariance first and then dimensionality reduction, because once you have a data set, you have to find the covariant matrix, which is it's very simple mathematical operation. I can cover it in less than 5 minutes, but maybe it's going to be a topic which we are going to see for sure in the future. Or before you go to the third year, it might be a good exercise for you to go over linear algebra and see once again, go over the major principles. So this PCA is all based on eigenvectors and eigenvalues. And eigenvectors. So now the same principles, we use them to cover this important topic, which was diagonalization, which as computer engineering students, you'll see it a lot, okay? And when you see it, I can strongly suggest to you to go back to major or basic principles of linear algebra. Actually, to some degree, you can consider this one semi-advanced linear algebra material. Because for a moment I thought, how is it possible you have not seen this? But I forgot just for an instance that you are still in second year, but in the future you're going to see this a lot. And that example, I really wanted to more remind you of this type of solution, because it all uses the information that you took in the first semester here at EPOCA. But don't expect a question like that in the final. We'll be including bonus points. And Eledio, I can ask bonus, yes, I think you may deserve a couple of bonus points, but do you want bonus points? Okay, I can promise also you a few bonus points for the final. It won't be, the exam, it will not be over 100, okay? Expect a slightly higher points, yeah. Yes?
Are we going to have to solve differential equations using Euler's method, Kuhn's method, and the midpoint method?
Yes. Prepare yourself for it.
For all three methods, or maybe just Euler's method?
No, I don't think, actually asking all three methods in a limited amount of time, in the order of 2 hours, we cannot ask the other topics, okay? So not all of them, but
So it will be up to us which method to use. It will be up to the students to select the method.
Actually, let me decide on that. It will be even up to me, okay? But I think all of these three techniques, they are very similar, okay? But
right.
If I ask you, let's say, you might get a question like this in the first question, where I said to you that you might expect also theoretical questions. You may even be asked, actually, what is the difference between the Euler method and Kuhn method, okay? Or Runge-Kutta method? What are they doing differently? Actually, I said a couple of times, even in today's class, actually. I've said this more than 5 times. I might have become boring even when we did differential equations. So they are all similar. There is a slight difference between all of these. Expect to see a question like that in the final exam. And if you think that for either method you don't remember the formula, if it's something straightforward, okay. If it's not very straightforward, I can give you hints, okay.
All right.
At least in the numerical method, which is a very complex 4-step calculation for each subsequent data point.
Stiffness and multi-step.
Sorry?
Stiffness and multi-step for differential equations. Do we have to study these topics as well?
No, stiffness no, but stability yes. But for example, you remember that we discussed in the class, and it is very important, okay. But I don't expect actually. So at least this stability discussion, which if you remember, it was strongly depending on the value of h, okay. So we have this. You can find this in the class recordings where we discuss this topic, but you might not. How can I say? Stiffness probably not, but stability yes. Any other question? Okay. I hope you had fun doing the last homework. And also I hope you also learned something more from the last one. Okay. Then if you don't have any more questions, we can closely end this session. We can slowly close this session. Okay, so I thank you for your attention.
Professor, may I ask one last question?
Yes, sure.
Concerning bracketing methods and open methods, are the graphical methods, bisection method, false position methods are included, right?
Yes.
What about Brandt's method in open methods? Do we have to learn that as well?
Well, so in the exam, you are expected to bring a calculator, okay? And let's see actually how these graphical methods, how this can help us, or how we can approach a problem fast. For example, assume that I have a polynomial or any function. Let this function f be equal to 3x e to the power minus x plus sine of 4x minus 7. Okay, so we have to find the root of this function. Then I say to you, okay, find a bracket, find a candidate point for a root. So what you can do is that, you can start like this. Set x equal to 0. Set x equal to 1. Okay. You substitute these values. If the sign of this function is differently, then it looks like this function, it has a 0 somewhere. So let's substitute x0. This is 0. Sine 0 is 0 minus 7. So here the function for x equal to 0, this is equal to minus 7. Good. Now let's set x equal to 1 here. This is 3 times 1 over e, because e to the power minus 1 is 1 over e. So this is 3 divided by 2.7. So let this be approximately 1. 1 plus sine 4. What is sine 4? 4 is actually radian. Okay, so in your calculators, please be careful. What is 4? I don't know what is 4, but I know that 360, or let's do it like this, 180 degrees. This is equal to, what is this, pi or?
It is pi.
This is pi, right? Or this is 3.14 as a numerical value. Then here, sine 4, it's something here, okay? It's in this quadrant, which looks like, but it's smaller than 1. So here, let me say here, f when x is equal to 1. Now, if you have a calculator, you don't need to do this in so much detail, but this is something like 1 minus 0.5 minus 7. What is this? This is still a negative number. That's good. Which means that this is negative. So we have no root actually. So it looks between 0 and 1, we have no root. Okay. Then let's do x equal to 4. So or give it x equal to 5. You put x equal to 5, this is 3 times 5 is 15, divided by 3, this is 5, plus sine 5. What is sine 5? Actually, this minus 7, this ruins a lot of things, because, but no, I think we're good. 3, 5, sine 5 is still a negative number, minus 0.5, minus 7 is still negative. Okay, so it looks like at x equal to 10, so you can, I just pick a function like this, okay? So you can do a couple of tests to see where the sign of the function is changing. So when x is equal to 10, this is 30 divided by 3, this is 10. When x is 10, sine of 410, sine 40. What is sine 40? Of course, the calculator can help you a lot. But sine 40, it is 40 divided by 3. This is something like, or let's divide this one by 6. This is 36 plus 4. So we're going to be somewhere here. Check this one again, but we're going to be in this quadrant, which is minus 0.5, minus 7. But it looks like the solution, it's around 2, or 2.5, yeah, 2.5. So it's a positive value. So it looks like you have a root between x equal to 5 and x equal to 10, okay? You can make things with a smaller step by going midway. You can check what is the value of the function for x is equal to 0, x is equal to 7.5. So you cut this one in half, because here you have a negative sign, and here we have a positive sign. So you can attack this problem like this. But what is very important is the following. So if you do anything, provide an explanation. So I'm looking for a change of sign. Okay, write this down, because if I see it and you got something wrong, I know that you are aiming something reasonable, and you are going to get partial points. Okay, so if you try to imagine that you are showing this to one of your friends or to me, and short explanations, okay, like, okay, looking for a negative sign. I got a negative sign, I cut this in half, I'm using bisection method or something else, yeah. Arioli po, këtë regjistrimin do e vendos patjetër, do e vendos në, it will be shared, okay? So, I guess going a little careful over the class material should help you a lot, to some degree at least. Okay, so I think also this root finding, we try to answer also this one to some degree. Okay. Now, this polynomial that is on the board, maybe we can take out this minus 7, and you can try to solve this one using the Newton-Raphson method. Okay, give it a try and see what you might get. Okay, so I'm here for any other question that you have, that you may have. So you might always remember the following, that numerical analysis method, it's really a very good course, because a lot of analytical or presumably difficult integrals or transformation functions, or you have taken, I think you are going to take Brent's method. No, Kevin, I can say no to it, because it's because Brent's method is a mixture of two other methods, so don't. So Kevin, it's a no to the question of Kevin. So numerical analysis method, it really helps you to write in a discrete manner with small steps, as smaller steps as possible, in order to get a higher accuracy. So if you have an integral, which we can call this an analytical approach or an analytical solution, you may find a solution using discretization of the problem. Për pyetje teorike o Aniledio, po konceptet e përgjithshme për shembull. Çfarë është shikoni çka kemi diskutuar në klasë, më thënë çfarë, a ka pyetje teorike te këto provime që kanë publikuar aty te Google Classroom? Ka pyetje teorike aty se mbaj mend? No. Njëra s'pas kam duket. Okej, që ka diçka aty. Shikoni, është një midterm aty I cili kam kërkuar disa define, disa përkufizime. Është një midterm aty në sistem, në Google Classroom. Ndërkohë që jemi këtu në klasë, a mund ta zgjidh dikush të ushtrimin e dytë tek midtermi? Have a look. It's interesting. This midterm exam question. It's impressive. It happens that very few students solve it. Okay. Okay, so
Buy 100 hens.
What is that?
Buy 100 hens, and you got for $100 100 two-legged birds.
Let me see.
Because a hen is $1.
Yes, yeah, that's an answer, yes. Yes, I think you got it. But you have to buy, what if you have to buy at least one of them from all of them? So you cannot, you have to buy 3 components or 3 products, three different products with different prices. You can have a look again into that. Okay, so we can go over. So I was just looking at the questions. Sorry. Okay, so for any more questions we can. Ne mund të përgjigjemi, po dëshironi mund ta mbyllim me kaq. Okay, edhe një herë ju faleminderit dhe miru takofshim. Uroj të semetit të kaluar sa më mirë. Dhe të jeni sa më I mbështetur, mund të rekojmë gjithë çfarë. Bjorni do vendos një listë të temave të Google Classroom.